If we look at an example where the deflections for the 6 leads are provided, we can work out where the MEA lies. There are a number of methods to determine the MEA. Let's look at the isoelectric lead method. The isoelectric lead is the lead where the sum of the deflections equals a net deflection of 0. This would indicate that the MEA is lying directly perpendicular to this lead. Often the MEA isn't exactly perpendicular to any lead, so you would be looking for the lead with a net deflection that is smaller than that of any of the other leads. In this case, the isoelectric lead would be lead AVL, which has a slight positive net deflection. The small net deflection tells us that the MEA is situated at almost a right angle to lead AVL, whereas the positive value indicates that the MEA is pointing towards the same half of the axis as lead AVL's positive electrode. Taken together, this information indicates that the MEA is oriented in one of 2 ways. Next, you look at the lead that is perpendicular to the isoelectric lead. In this case, it would be lead 2. Lead 2's deflection is strongly positive. The positive deflection indicates that the MEA is pointing in the direction of lead 2's positive electrode. If we combine this assumption with the information provided from the isoelectric lead, we can determine that the MEA lies on the less than 60-degree side of lead 2. With the tall R wave method, we identify the leads with the strongest positive deflections. The MEA will lie somewhere between these 2 leads, pointing in the direction of their positive electrodes. In this example, leads 2 and AVF have the tallest R wave, with lead 2's being slightly taller. This means that the MEA lies somewhere between leads 2 and AVF, pointing towards their positive electrodes. Lead 2's R wave is slightly taller, so we can infer that the MEA is slightly more parallel to lead 2 than it is to lead AVF.